No. So in probability, what is meant by exhaustive events? So events are said to be exhaustive if their union is an entire sample space. That is, if E1 and E2 are two events of the sample space, yes, and their union is yes, then E1 and E2 are said to be exhaustive events. Next, mutually exclusive events. Events are said to be mutually exclusive events if their intersection is a null set. That is, E1 and E2 are two events of the sample space, yes, are said to be mutually exclusive if E1 intersection E2 is a null set. Next, equally likely events. Events are said to be equally likely if none of them is expected to occur in preference to the other. That is, in throwing a die, all numbers 1 to 6 are equally likely events. A pair of dice are rolled. So the sample space contains 36 elements. Let us consider the event A as sum of the numbers is greater than 8, and B is the event such that 2 occur on either die, and C is the event sum is at least 7 and a multiple of 3. So these are the elements of the ordered pairs A of the event, and ordered pairs for the event B, and ordered pairs for the event C. Now when you calculate A intersection B, there is no common element at all. So intersection B is a null set. So you can conclude that A and B are mutually exclusive. B intersection C is also null set. So B and C are also mutually exclusive. But whereas A intersection C is not a null set. So A and C are not mutually exclusive. Probability is a function which assign a non-negative real number from 0 to 1 to every element of the sample space. What is axiomatic definition of probability? Let S equal to W1, W2, W3 and so on Wn be a sample space, and Wi, I equal to 1 to n are elementary events. So a function P which assign every event A subset of S to a unique non-negative real number P of A is called probability function if it satisfies the following conditions. So first condition is probability of Wi must lie between 0 to 1, where I equal to 1 to n, and sum of all probabilities must be equal to 1, that is sigma I equal to 1 to n, P of Wi equal to 1. Also, if A is any event subset of S, then P of A equal to sigma P of Wk, where Wk belongs to A. That is, all those elements of the set A, for that sum of all the probabilities becomes your probability of the event A. So if it satisfies this, then only we say it is a probability function. So consider the sample space S equal to h comma t. Now you have to identify whether these are probability function or not. First bit, P of h equal to 1 by 2, P of t equal to 1 by 2. So each lie between 0 to 1 and the sum is 1. So it is a probability function. P of h equal to 1 by 4, P of t equal to 3 by 4. So here also P is a probability function. Whereas third problem, P of h equal to 1 by 8, P of t equal to 3 by 8. Even though both lie between 0 to 1, but the sum is not equal to 1. So P is not a probability function. Another one is classical definition or mathematical definition of probability. Let S be the sample space and E be any event of the sample space S. That is, E is subset of S. So probability of occurrence of the event E is denoted by P of E and defined as P of E. That is probability of the occurrence of the event E equal to number of favorable outcomes of the event E upon total number of outcomes of the sample space S. That is P of E equal to N of E upon N of S. When E is subset of S, N of E will be less than or equal to N of S, and N of E greater than or equal to 0. So from this you can conclude that probability of E lie between 0 to 1. Then probability of non-occurrence of the event E, that is probability of E complement, which is equal to N of E complement and upon N of S. which will be same as n of s minus n of e upon n of s. So if you separate the terms, you'll get probability of e complement equal to 1 minus probability of e. That is probability of e complement plus probability of e equal to 1. Also probability of e complement lie between 0 to 1.